Hello, everyone. Come on in. I didn't want to wait till the last minute to send you the link to the to the Zoom page. Hopefully, everybody's getting. I completely forgot I hadn't sent out the link to the Zoom page. So, yeah, you guys are getting it literally like what 20 minutes, 15 minutes before the class started. Glad you're able to find it. We're supposed to have, I think, 15 people in the class. We've got 4 of you guys are so awesome. You're already here. And I use the phrase "guy" to refer to everybody, whether it be a male or female or other. Waiting for a couple more. Anybody have any questions while we wait? You can unmute if you'd like.
Sure. I have a quick question about Canvas. Are we supposed to be logged into Canvas now?
You can. I literally just published it a few minutes ago, so you probably might not have seen it before when you're in there, but you can now, and it's got a lot of extra modules in it. They took a long time to copy over from my old course, so you'll see stuff that's not necessarily relevant as far as the dates go. But by tonight, the first week will be set up with your assignments and everything like that in it. The syllabus is there as well. That's what I'm going to go over for starters in class tonight, and then we're going to go over chapter 1. But you do not have to go through you don't have to go through Canvas to get to Zoom, but I think that's the way most people do. I put a link to it on the page, but I also send everybody an email, so you can just click on the invitation to the email, and that'll take you there as well. How did y'all come in?
I had somebody send me the link, and then you also sent one through email, so that works too.
Gotcha. Yeah. Okay.
But on Canvas, I currently don't have the class, so I'm wondering maybe if anybody else has that issue.
Let me double check to make sure I did. I clicked on publish, but you know how that is. Don't matter what you did.
Yeah, my class just showed up probably like within the last 15 minutes.
Okay. Yeah, and sometimes if you don't see it, even though other people are seeing it, that just needs you to back out of Canvas and then go back in it. Sometimes you might have to zap your cache, but that should be there now.
Sounds good. I'll work on that.
Okay.
Thank you.
At the end of the module, it says Tidewater Community College. There's a link to Zoom meetings. That's where I put, I think that's where I put the link to this class. Yeah, that looks like it. Okay. We still only have 5 people, but that's, like I said, that could very well be because they didn't get their email or you didn't see the Canvas was open and all that good stuff. Let me send one more email. I'll send this one through Canvas though, so maybe that'll help. And then we'll get started. We're actually got more than enough time today. You're probably going to get out a little early, and I'm okay with that. So I'm sure you'll be really, really, really upset. So I'm going to go to inbox. There it is. Okay, got that. Okay, I'm gonna send this to everyone. So I just sent this one through the Canvas email because I don't know which email students are necessarily paying attention to. So I thought it might be best to send it through both. All right, starting the course. So if anybody takes a little time, hard drive, you guys, when you're watching, so the picture should look fine there. So that's why I do that. But right now, you might actually not be able to see good images. It might be lagging if I write for that. Still not in Canvas. Nora's still not seeing it in Canvas. Yeah, try emptying your cache, Nora. And actually, let me check and make sure you're actually.
I emptied all my cache and like the search history, all of like my internet history, and then relogged into everything.
It still didn't show it. There's a way you can set up the dashboard where it shows all courses as opposed to just starred ones and some weird stuff like that. You might want to check that setting. I'm going to check and make sure you're listed as one of my students.
Okay, because I was just enrolled in the class like last class period, so we were in our lecture or our lab. So that might be what's
going on. Yeah, I'm checking that right now, and I'm actually killing the bandwidth. That's why it's What was your last name, Nora? Wilkerson, right?
Wilkerson, so yeah.
Way down the bottom. Yeah, you're not listed in there yet. That's why you're not seeing it.
All right, that makes sense. So it'll take a minute then, I guess.
Yeah, when you get it, sometimes it takes till midnight. I would hope they're going to get it quicker than that. But if you don't see it after midnight, then make sure you contact help desk for consistency. In the meantime, you can look my. Let me go ahead and give you guys this. So I'm going to turn on my document cam. And I'm going to give you my YouTube address because this YouTube address is where I'm publishing everything. So my YouTube page is www.youtube, and I write in small caps. So if they're tall letters, they're capitals. If they're short letters, they're not capitals. / Billy Younger Physics Solutions. So if you go to that website, you'll see a ton of titles there. There's literally a class for every class in 241 and 242. And you'll notice they actually have a name that's based on the date and stuff like that. In the Canvas page, when you get there, you will see a link to my Google Docs page. And what I've done is I take these notes when I write them, I take photographs of them, convert them to PDFs, and upload them to my Google Docs. So all you have to do is look up for the day. Look, there'll be some file that says 052322. And you just do a search for that. And if it's a 241, then you're in the right one. It might be for a 242, but I think this semester I have only 241s on Mondays and Wednesdays and only 242s on Tuesdays and Thursdays. So you shouldn't even have to do that. But if you subscribe to the page, it'll also, you can set up the notifications where it'll let you know every time I post something, because I don't always post something just right after class. Sometimes I get a little spare time and I'll work a couple problems, maybe based on something the student asked me or something like that. So you can always check that. So everybody get that. There's if you don't, for instance, especially you, Nora, since you don't yet have Canvas, this email address, this URL will let you get there. Okay. All right. So turn it back to the regular document. To my regular camera. We're covering introduction, measurement, and estimating. So this is chapter 1. What we're using is Giancolli's 4th edition of Physics for Scientists and Engineers with Modern Physics. See that modern physics part there? I don't care if you have the latest version, which is actually there's a 5th edition out now, but we haven't switched to that. So we're still in the 4th edition. I don't care if you're using a 3rd edition. So if you want a physical hard copy, but you don't want to pay, all that money, I don't mind you using a physical hard copy that's a 3rd edition. You're not going to lose anything from it. So that's one way to save some money. You can also purchase either at the student store or directly by clicking into Canvas and clicking on My Lab and Mastering or one of the My Lab and Mastering assignments. And it'll make you create an account if you don't already have one. If you do have one, you have to enter your email and all that good stuff. But when it gets there, it'll ask you for your passcode, and that's the code that says, hey, I've paid for this. Or they'll let you do a free trial for 2 weeks. So even if you don't have the money right now to get that, you don't have an excuse for missing your first assignments. But you will want to go on there, and they'll give you an option at that website as well. So you don't have to actually go to the student store if you don't want to. You can buy it straight from there, and it might even be cheaper. You need access to MyLab and Mastering for Giancoli 4th edition, Physics for Scientists and Engineers with Modern Physics. And one version comes with an e-text, and that's all you have to have. You don't really have to have a physical copy of the book. But if you wanted a physical copy and you still want to save money, you could do that and then have then buy a 3rd edition from eBay or something like that. But you can also just buy the access to the web assign, the MyLab and Mastering homework set, and that'll allow you access to the homeworks, which counts as a part of your grade and that sort of stuff. So you got to have that as a bare minimum. But if you buy it with the ebook, then that's probably the cheapest route of getting this edition with the appropriate homework thing. Okay, everybody understand that? Let me share my screen for a second. Okay. So right now I'm looking at everybody's names. Basically, there's no grades in here, so it's not any danger of messing anything up. But the main thing is I wanted to show you what the Canvas page will look like. So you'll see, so my bandwidth is going to poop. When you go into this stuff in it, they're called modules for students this summer, semester, and it automatically got copied when I took that course information. So what I'm going to do is delete this whole thing. Actually, tricky. Okay, so I'm going to put this very, very important video on the syllabus. I'm going to put that there, and this is our actual syllabus in PDF form. So I'm going to put it up there too, if I can get a hold of it. Okay. These helpful documents and links are good to go. Okay, now I put that in the wrong one, so let me now move this up to the right one. So that is one way you can click onto Zoom meetings. I'd like somebody to give that a try, maybe next class, so I can see if it actually works well enough for you. You can just report back to me on that. Here is your syllabus. We're getting ready to go over that in a second. Now I see I can get rid of this because I've gotten the stuff off of it that's important. I'm going to delete that. The next part is where I've copied from the previous course as well. And you'll see the old syllabuses and stuff like that. So these are all documents when they got these little paper clips here. You can tell by the dates that they're not useful. Okay, they're not this semester. So they will be emptied in a second. These ones that aren't showing here, you won't see them at all. You'll just see these guys that are here. But this is a list as of January 12th, a list of my YouTube videos by title, and the title is usually sufficient to help you understand what it is. I'll probably be updating this throughout the semester. There's the link to my YouTube channel, Billy Younger Physics Solutions, and here's a link to my Google Docs where the notes for each of those will be. All right, got another student coming in. All right, this is where all the practice tests will be. And I want you to have access to practice test 1 right now, but not to all the other ones. Okay, you can see I'm going to have a practice test for essentially every test you take. And then I will have a test available. And you actually get credit for taking those practice tests, where basically I take the average of all the practice tests at the end of the semester, divide it by 20, and that number of points is added to your course grade. So this is where you'll find those practice tests. Our tests this semester are face-to-face. They'll be done in your lab. I know you guys supposedly have Kevin or Mr. Mitchell for your lab instructor. And I'm sorry for not letting y'all know before this. I was thinking for some reason that your lab met after this class, not before the class. So that's why you didn't have any information about it. I apologize for that. And I'm going to hide that too, maybe. Okay. So you'll see week 1. This is all the stuff about chapter 1. In fact, what I'm going to have here is chapter 1 and 2 all up here by this evening, because in the first week online, you're basically on the summer course, you're basically going to cover 2 chapters a week. So this week is no different. So you'll have those. These are old lectures and some of them are actually still in Canvas as opposed to being on my YouTube channel. So they'll have the password at the end of them. So you need to copy that password when you try to click on it, if you decide to use it at all. But it has videos. There's the significant digit rules. Here's a YouTube video where I teach you why sig figs fail. Here's a lecture on unit conversions. And here's a lecture on the scientific method and notation. So all these are videos that can help you, for especially if you had to miss class, or you missed the first minutes of class because I was so prompt in getting the links to you on time. But as you can see, the rest of the semester, the weeks will pop up one by one by one. And they'll always have videos in them, or links to videos, and they'll always have homework assignments in them. The due dates are always, except if I tell you explicitly, is always going to be basically 11:59 on the Sunday before. So week 2 homework will be due, or week 1 homework will be due this coming Sunday at 11:59 p.m. The next one will be Sunday again. The next one will be a Sunday again. Sometimes a given chapter will have 2 sets of homework as opposed to 1. When I do that, sometimes I'll allow one of them to be due on Wednesday and the other one to be due on Sunday. So other than that, everything is always going to be expected to be done by Sunday. So that's how the class is going to work as far as homework goes. Now, what I want to show you is the syllabus. So I'm going to scroll up here to our syllabus in the PDF form, and now I want to explain that to you. Anybody have any questions about what I've told you so far? By the way, that's another way you can get to my lab if you want to go ahead and purchase the package to access your homework, or if you just want to start doing your homework, like I said, you get like a 2-week grace period. So you can click there, or you can click on one of the assignments. This is our course syllabus. Let's see if I can make it a little bigger so you guys can see it. Boy, that was big. Oh, there it is. Okay. The main thing I want you to see on this is my office phone number, and this is supposed to be 241 N01C, and when I typed in the N01C, it actually left off the quotation mark and left off the capital IN in front of instructor. So this phrase right here, without the quotation marks, that's going to have to be the beginning of every subject line of every email you email me. I need you only to email me from your TCC email address. My email is W as in William, Younger, YOUNGER, at tcc.edu. But I got a lot of filters set up because I get hundreds of emails a day and I can't afford the time to check them all. So if you don't have your subject line starting with PHY241N01C, then I probably won't even see the email, much less reply to it. I have traditionally had some difficulties. I have, like, a laptop, a desktop, iPad, and an iPhone. All of them have Outlook on it. And that seems like the most sensible way to do it, because no matter where I am, I'll always get my emails. But I've discovered what I think might be a bug with Microsoft Office. It might be a bug with Canvas. It might just be an idiot instructor that hasn't learned all the ins and outs. Specifically, one of those Outlook apps is removing emails from the email server when it looks at them. So if I look at one email server, I might actually not get your email because it's at another one that I didn't check. Like maybe it's on my iPad, and the iPad went ahead and downloaded the email and then erased it from the server. That's a setting, and in most computers you can find a setting to keep it from doing that. I haven't found them yet. So if you have problems and I don't get back to you on your email within one school day, so that means even if you email me at 1 a.m. on Friday, I am supposed to get back to you no later than 11:59 p.m. on Monday. Okay. But if you emailed me at 12:01 a.m. on Thursday, I have until 11:59 p.m. on Friday to reply to you. Okay. But if we see that there's a problem with that, I might actually do what I did last semester, which was give my personal phone number, and then you guys can text me if something like that happens or if it's urgent. So just keep an eye on that. I'll let you know if I actually have to do that. Hopefully I won't. It won't be a problem this semester, but who knows. This just tells you what the topics covered in the class are. what I need you to see really, all right, poor Ivan's having a hard time getting in here. I've put him in a bunch of times, but he's not coming. Okay, so this is our tentative schedule, and chapters 1 and 2 is what we're expected to cover in week 1. And usually I do, like I said, 2 chapters per week. I think next week, chapter 3 is a little tough, so I might use both days for that. Or no, it could be because Memorial Day is Monday and we're not actually meeting on Monday. Notice this semester we have 3 Mondays off. We have Memorial Day, we have Juneteenth, which actually technically is June 19th, but they wanted to give you that day off anyway, so they canceled classes on Monday, June 20th. And then finally, we're off for July 4th, which happens to fall on a Monday this semester as well. So you can see where the chapters are covered. This is the time that the assignments are due unless I state otherwise. So you can see them there. These are when your tests are occurring. Your tests will be administered to you via Canvas in the lab, and Mr. Mitchell will be watching over you, making sure you follow the rules and all that good stuff. You're not allowed to do internet searches. You're only allowed to have blank paper and an equation sheet. And the equations I allow are only the equations that are numbered in the book, unless I explicitly tell you otherwise. So it's your job when I tell you, hey, this equation is not numbered in the book, but you can use it on your equation sheet, you need to immediately write that equation down and highlight it so you can find it later to put in your equation sheet. But these are the dates of the test. You can see all that, the last date to withdraw, so on and so forth. The final exam, which is actually going to be on August 1st during your lab time. Okay. Here's the attendance policy. If you do have to miss several days in a row for something, let me know ahead of time and I can probably work with you. I might have to, do some kind of legalese thing where I tell you, missing this many classes is bound to make you have a high probability of failing, but I'll let you do it anyways instead of dropping you. Okay, so just keep that in mind. Generally speaking, your homeworks allow you to turn them in late, but you're losing like 5% per day. So even if you got 100, if you turn it in 2 days late, you're down to a 90 already. So you want to make sure you don't do your homework late. You want to make sure you do it on time all the time. Okay. I've never really had any issues with students misbehaving, so I don't have to cover that too much. The main thing about electronic devices is if Mr. Mitchell or I were to catch you with anything other than your scientific calculator, and you can use a graphing calculator, I don't mind that either. But if you have a graphing or scientific calculator, you can have that out, but you can't have, an iPad or anything else that can access the internet out. Even if you just happen to feel your phone vibrate and want to make sure it wasn't your mom, you're not allowed to pull your phone out during a test. And if you pull your phone out or an iPad or a Kindle or a niche or whatever, any of those things, if you pull them out during a test, we will assume that you are cheating and you're going to get a 0 for that test. We might even drop you from the course. So just don't do that, okay? We're trying to make it as easy on you to understand as possible. Just don't have it out and nothing will happen. Now, that being said, I know I get a lot of military people and sometimes they're on duty. So if they go to the instructor before class and say, hey, Mr. Mitchell or Mr. Younger, I'm on duty and the government's requiring me to be at the ready for any kind of emails or text messages or something like that I get. So will it be all right during this test to have my computer or my phone on the desk? And I'll say, yeah. And then there's a good chance that basically I'm going to have you walk out of the room to answer it. And I might stand by just to make sure it's not anything, test related. It won't be, of course, but still just that kind of thing. So just let me know. I'm not as mean as it sounds. I just got to protect the sanctity of my classroom so that I know the people that are doing the test are actually the people that are getting the grade. All right, here's my grading policy. You can see I'm basically on a 10-point scale, but I give you an extra point to make it to that D mark and to that C mark. So instead of a 69.5 or higher to get a C, I allow a 68.5. Similarly, to get a D, I allow you a 58.5. The tests, I'm going to drop the lowest one. I may actually have some online tests or online tests. Sometimes that's nice to throw in there because it's one that students are allowed to use their book. They get multiple chances. They're allowed to use their notes. They're even allowed to Google. It'll just be limited by time. So if I put one of those in there, that will count as one of the tests as well. And that actually tends to bring students' grades up. But I still drop one lowest test grade. I don't drop any of the lowest conceptual homework grades, but I do drop the 2 lowest homework grades. Okay, so the 2 lowest homework grades are automatically being dropped. If I give you an extra credit problem, like I'm probably going to give you today, then you're allowed to turn that in as extra credit. And what it does is it ups this number from 2 to 3. If I give 5 of them, it's going to up this number from 2 to 7. So that's how my extra credits work. Except for the practice test where I get basically up to 5 points added to your final grade based on your average highest of all your practice tests. Okay. Word to the wise, basically colleges and universities generally do not believe in giving practice tests. Okay. If you ever find a college or university instructor that has taken the time to make up a practice test for you, you better move heaven and earth to get that done, because that student, that teacher has really put a lot of work into it, and he's doing something that they sort of would be frowned upon within his community. So he must have felt it was the only way to help his students. So make sure you take people up on that. If you're in a college class and they take the time to give you a practice test, make sure you work that practice test over and over and get help with it as you need. No different in this class. And in fact, these practice tests that I give you in my class, I'm going to stop sharing now. As soon as I can find the stop sharing button. Can't find the stop sharing. That's not helpful. I think I covered it up with something. Whoa, kill that. Did I put it over here maybe? Where'd you go? Oh, letting in another student. That's cool. Normally there's a nice little button around here that says stop. Oh, there it is. Found it. Ooh, okay. Now, so now that you've seen that syllabus, what I want to tell you is these practice tests do count for you. And not only that, I use the exact same bank that the instructor or that the author of the textbook uses or gives us when we adopt this textbook. So I use that to make the practice tests. And every time you take a practice test, it's only like 5 or 6 problems. It's supposed to last you like 10, 15 minutes, really not that long. But every time you take it, you're going to get a different set of questions. So if you were able to take it an infinite number of times, then you will have seen every question in that entire bank. And if you memorized or learned how to do every one of those problems, I guarantee you get at least an 80, but maybe even as high as a 90 on the final test, because I guarantee that 80% of the points on a given test are available to the practice test. So that's yet another reason to make sure you take the practice test, is because 80% is a really good grade, and I give you access to 80% of the points. And my reasoning behind that is usually my bank for a given practice test is over 100 questions, maybe 150, sometimes 200. And even if you happen to not have figured out how to solve one of those particular problems, if you figured out what the right answer is, you're getting paid off in dividends by doing well on that particular question. And I don't feel bad, because chances are you probably learned how to do most of the other ones. And if this one you just happen to memorize that and figure it out, so what? You got lucky. Okay. So I feel justified in doing it. And I just want to make sure you guys know you should probably take me up on that. Oh, Sarah, Nora was letting somebody know something on the discussion board. So make sure, Sarah, you got your laptop from the lab. Mr. Mitchell will be there for you anyways. All right. So that is our syllabus. Anybody have any questions on how that works? Okay, so just remember, you should expect at least every Sunday by 11:59 p.m. you're going to have probably at least 2 assignments due. Most of the time it'll be 4. There'll be a conceptual homework for 1 chapter and a problem solving homework for that same chapter, and then another one for the other chapter. So there would be like 4 on a normal week. Next week, we're only doing chapter 3, so that might only be 2, but you're always going to have some due. Some chapters have 2 sets of homework problems for that one chapter, in which case I try to give you a little extra time by, say, making the 2 homeworks due on Wednesday instead of the Sunday, where the 2 concept homeworks will be due on the Sunday. So just watch out for that. The due dates on MyLab and Mastering are always the correct ones, at least once we've covered the chapter. So sometimes you can look ahead and you'll see homework dates, and they're like due right now, and we're in chapter 3 and this is chapter 9 that's due. You know that one can't be a correct date. So that's what I mean. As long as we have covered or are covering that particular chapter, then the date on MyLab and Mastering is the correct one. All right. So let's now, again, anybody have any questions before I get started? Okay, so the first thing I want to start off with is talk to you a little bit about the nature of science, and I do it a little differently from the way your book does. So you still need to read the chapter so you can make sense of the concept questions as well as the practice test questions, because they ask it more from the scenario that the author provides in the textbook than mine, obviously. But I'm going to show you my way because I think it gives you a little deeper understanding. All right. So I see the scientific, quote unquote, scientific method as this cyclic process that never ends. And I see it as sort of 3 parts. One part is the observation or the experiment or something like that. And I usually just call it observation. And then from that, you make a hypothesis. And I'm going to draw this on this piece of paper in a second. From that observation that you made, maybe you're looking out at a park and you see a kid throw a rock, and they do it kind of goofy because kids are morons. So they throw it like with a straight arm, and it looks like it goes almost half, like a quarter of a circle. So a hypothesis only has to be falsifiable to be a scientific hypothesis. It doesn't have to mean the hypothesis you're making is some way reality. It just has something common that allows you to make predictions with it, and that can be falsifiable. That's all you have to have a scientific hypothesis, is for it to be falsifiable and allow you to make predictions. So your prediction might be, well, it looks like when little kids throw balls with their arms straight, the balls follow out a path that looks like the quarter of a circle. And the radius of that circle is basically the height from the bottom of the kid's foot to the height of the rock in the kid's hand. So the kid does this and releases it. It's going to take off horizontally. The radius of the circle. You might even say it travels at a constant speed. And you might take a couple of snapshots of just as it leaves his hand to get an idea what that speed is. And then you'd predict where it's going to be at any time thereafter up until it hits the ground. By pretending that rock is really on, say, the axle of or on the outside edge of a wheel that's rotating at a certain meter per second of circumference, you've actually made something that's falsifiable. In other words, if I do the experiment and I get it wrong, then it's false. Okay. But it also has the ability to predict, because you can say, okay, well, it goes through a distance s, which is given by r times theta. But the s is given by velocity times time. So you can always predict at what angle it will be at any point in time. And therefore, you make a prediction that at 1/2 of a second, it'll be at such and such a place. At 1/3 of a second, it'll be at another place. And then you go back and observe again. Now, if that turns out to be right, you're not finished. You just got something that bears some resemblance to reality. So you do it again, make another prediction, and again, make another prediction, and again, and you keep on doing that. And as long as it keeps coming back right, then you're building what's called a theory. And this is the modern version of the word theory, which is a highly supported paradigm of thought about a particular problem. Now, it could be a single simple hypothesis, like when the temperature goes up, the pressure goes up, right? That's just one single event sort of thing. or it could be something big like the general theory of relativity, which has all these bells and whistles and they tell you all these different things, but still it's a hypothesis until it's been verified numerous times, and then we allow it to graduate to what we call a theory. In the olden days, they would say we've allowed it to graduate to what we call a law, but that sort of smacks the scientific revolution in the face, okay? The reason that we were kept at bay and didn't learn anything new about the universe for 2,000 years was because Aristotle had essentially made up the laws of physics, basically out of whole cloth. He was just a brilliant man and was able to do it. And he did it with some very precise premises that he thought were completely obvious and need not prove them, okay? And then he used really fine logic to make those premises, make predictions, and lo and behold, it worked. In the intervening period, Christianity became a power around the world. Emperor Constantine was the one that started that, of course. And by the end of, say, 1,000 years after Aristotle, everybody had went ahead and interpreted the entire Bible as created by the Council of Nicaea in terms of Aristotle's thought. Now, everybody was afraid to mess with Aristotle's theory because Aristotle was this giant mind from the history of the universe, and we knew he was brilliant. And not only that, the whole church had adopted everything from Aristotle to make sense of the Bible. So because those two things were intermingled, it made it very hard for science to progress outside of the Aristotelian thought, which was dead wrong, okay? Aristotle had basically a geocentric, not a geocentric universe, but a geocentric universe, not a heliocentric universe, which is a more close to the modern analogy. Of course, we've since figured out, since Hubble did his first observations, Edwin Hubble, not the Hubble Space Telescope. When he did his first observations, we realized that the universe was not just the planets that we see and the stars that we see. There turns out to be a bunch of islands of stars like ours, ours is called the Milky Way galaxy. There turns out to be 100 billion of those. And each one of those is on average about the size of our galaxy. So there's 100 billion stars in 100 billion different galaxies. That gives you 100 billion times 100 billion, or 1 times 10 to the 22 stars in the observable universe. Before that, we just thought it was maybe that those 10,000 or so stars you see throughout the year from a very dark place on Earth, and the planets that are orbited us. So Aristotle had taught a geocentric universe was the existence, and then we had to make sense out of data as it got more progressive. But so you could take Aristotle's idea, which was that here's the Earth, here's the moon orbiting about it, and then here's the sun orbiting about it. And then outside of it was Mercury and Venus and Earth. And actually some versions put Mercury and Venus before the sun, and then Jupiter and Saturn, and that was the entire universe. But his predictions weren't really quite correct because he said the heavens are immutable. That was one of his premises, is the heavens are perfect. And that means they can't change, because if they change from imperfect to perfect, which neither the imperfect part was never acceptable, or they change from the perfect, which is acceptable, to the imperfect, which isn't acceptable. So that was how his science was done. And since the universe is immutable, you can't actually change that stuff in the heavens. In other words, the stuff beyond the Earth's atmosphere. And that place varied. Sometimes it was beyond the Earth's atmosphere. But when you came back with them and told them something's changing about the moon, and they might put it outside of the moon, neat little things like that. But without the ability to change to match the data, you would have had a completely dead science. But luckily, what they were able to see is, well, hey, maybe Aristotle's right, but there's something weird going on. Namely, Mercury never goes more than like 38 degrees to the east or to the west of the sun. And Venus never goes more than like 47 degrees to the east and west of the sun. So they next had to change that up a little bit. So what they did is they put the Earth at the center, moon orbiting it, and then there was a epicycle and a deferent. The epicycle was a little circle on the deferent. So the deferent would have been the original Mercury in orbit, but then they put a circle on that, the center of which laid on that deferent, and Mercury would actually orbit around that spot while that spot moved along an imaginary line that connected the center of the Earth to the center of the sun. And you could adjust the radius of that epicycle so that it would actually match the 38 degrees or whatever. Then they had to do the same thing with Venus. That required a bigger model. You had to set just the right speed for the rate at which it goes around the circle. And then that would allow you to predict things. And you could literally go years in advance and predict where the planets would be. But maybe by after 5 or 10 years, you'd have to regroup and see if it still works. And lo and behold, you'd fidget some things. Maybe you tweak the radius a little bit. They ultimately decided that it's not going to be a circle. It's still going to be a circle, but the place from which you have to look at the orbit such that it's going at a constant speed is this equant point. And that equant point isn't at the center of the Earth. So it got really, really complicated. But that ability to change it is the strength that the modern idea of a theory, as opposed to calling it a law, has. By calling it, by refusing to call things laws, we're basically saying nothing's ever 100% true. We have to say it's sort of tentatively true. And Einstein put it this way. He said, no number of experiments can prove me right, and it only takes one experiment to prove me wrong. What he means by that is, yes, in fact, special relativity is the single most tested theory in the history of mankind, and it's never once been wrong. I would say it's probably on the order of billions and billions of times it's been tested, because basically when you run particle accelerators, the particles travel near the speed of light, so the laws of relativity are in play. Computer programs have to watch these collisions of these particles because there's so many, they're so small, they happen so rapidly that a human couldn't watch them all. So they write computer programs to look for anomalies that they're looking for. And then the computer would, of course, spit one out if it violated relativity, or if it appeared to be a particle they'd never seen before came out of it, stuff like that. Well, it's not uncommon for you to have hundreds or even thousands of collisions like that every second when an accelerator is running, and the accelerator will run for months on end. And there's hundreds or even thousands of accelerators all around the planet. And they've been doing this since, 1930. So there's never been a theory more tested than special relativity. But all it takes is one experiment to show that it's wrong. As long as someone can replicate that and make sure that the other person did it properly, then you have to throw that aspect of special relativity away. Even though it was this robust theory that's been tested billions of times. Now, we also have this thing called the correspondence principle, which Bohr gave us. Bohr, the guy that gave us the first model of the atom with regards to quantum mechanics. Bohr said there's a correspondence principle that we should adhere to. And what that means is, like, we've been using Newtonian physics for a long time by the time Einstein came up with general relativity. Well, the correspondence principle, which Bohr told us about, would suggest that if you take general relativity and you say that's the thing that's going to reproduce or replace Newton's laws of gravity, then in the realm where Newton's laws of gravity was correct, that general theory of relativity better reduce back to that Newtonian physics. And it does. Okay. Same thing with special relativity. That's got to reduce back. Same thing with quantum mechanics. In the area where we're talking about macroscopic things, quantum mechanics better give us the exact same equations that Newton did. So that's how we keep these things consistent. So when I say Einstein will be proven wrong, there's going to be some little aspect of relativity that would be proven wrong by this latest experiment. But the rest of relativity still has to be valid in the sense that whatever we replace it with has to match Einstein's predictions wherever Einstein was right. Okay. So let me draw that figure real quick. I'm going to turn on my document cam again. Maybe. Okay. So my picture of the cyclic process of science is observation. So you observe something, you hypothesize, and you use that hypothesis to predict. And then that prediction has to be observed again to make sure you're right or wrong. The main thing is this has to be falsifiable. It doesn't have to be provable that it's true. It just has to be falsifiable. So for instance, in my conceptual physics class, one of the questions that pops up from time to time is which hypothesis is scientific? And one of the choices is the moon is made of cheese. And students always think that's not a scientific hypothesis, but it is. All you literally have to do is just take a spaceship to the moon, eat a big wad of it. If it tastes like cheese, then it's cheese. If it doesn't taste like cheese, you know it's not cheese, right? So it doesn't have to be, you know, down to earth or reasonable. It just has to be falsifiable. Can I test it and get a true or false answer? Okay. Now, from that hypothesis, you use that hypothesis, which might be a mathematical model like the wheel representing the rock thrown by the little child or whatever. You make a prediction. And then that prediction, again, has to be true or false. In other words, you got to definitively be able to say, hey, what is successful for this prediction and what is a failure for this prediction? And then you go observe or run an experiment or whatever to test that prediction. If you go through this hundreds of thousands of times, you're starting to build a full theory as opposed to just a hypothesis anymore. And that's what like the general theory of relativity has done. That is what the special theory of relativity has done. That's also, believe it or not, what the Newtonian theory of physics or Newtonian physics has done as well, except we found regions mainly dealing with things super fast or things super small that Newton's equations don't work. But that's okay. We filled that back in with quantum mechanics for the very small and with relativity for the very fast and also for the very massive. But once it's gone through here hundreds of thousands of times, it becomes a theory, but it still only requires one experiment to prove it wrong. Does that make sense to everybody? Anybody have any questions about that? Okay. Now your book talks about models, theories, and laws, and he says a little bit different language, but I wanted you to have this paradigm in your mind where something's going around in a circle and you don't ever stop testing it. Okay. We're going to continue to test the theory of evolution day in and day out. It's constantly being tested. Just 10 years ago, someone made a prediction based on a fossil that they had here and a fossil they had here that differed by hundreds of thousands of years. Okay, they suspected that this one was a descendant of this one. So they predicted like mid-span between those years should be a transitional species, and they predicted exactly what features it should have. They described in some detail what, if any, feet it had, what, if any, fins it had would look like, what part of the soil you'd find it in. And then lo and behold, someone went out and dug and they found something called tiktaalik. That is the way a hypothesis that originally was the theory of evolution became a theory, became a full-blown theory now, and it continues to make predictions as it did there and then was proven right. Okay, and yes, there's a way to falsify it. It's, you just, you know, the famous quote is, show me a rabbit in the Precambrian. Because the Cambrian explosion is basically when things started to get hard matter to them, hard shells and stuff. So fossilization was super easy. But they were single-celled organisms mostly. And if you find something more advanced than a single-celled organism in a strata of soil below the Precambrian, then you've sort of turned you've sort of turned evolution upside down. Okay. Now, the next part we're going to talk about is measurement and uncertainty, and I'm going to use some demonstration stuff for that. So I have a pretty good little meter stick type thing here. It's not a meter stick, but it's a centimeter scale at least. And you can see the light kind of reflects a little bit too much. So I'll hold it this way. You can see it goes, for starters, notice the 0 is not at the end of the ruler. That's a good thing. And the end is not at the end of the ruler either. That's also a good thing. The reason being is if this edge represented 0, that edge could get mangled all to crap, and then you wouldn't know where 0 really is. But by having it over here, you do know, and it gives you some buffer. But when you look at this, you first need to say, okay, well, what are the units? Well, it says clearly there 1 centimeter, and then it says 2, and then it says 3. So these whole numbers are evidently measured in centimeters. And then you say, okay, well, how many spaces are there between, say, 1 and 2? Well, if you count those little spaces, you'll say there's 1, 2, 3, 4, 5 spaces, and then a slightly longer line than the other ones. And then there's 5 more spaces. So there's 10 spaces in total between the 1 and the 2. So each one of them must be 1 centimeter divided by 10, or 1/10 of a centimeter, which is also called a millimeter, by the way. So you can very definitively tell whether something is 1.1 or 1.2 centimeters. If it's 1.1 centimeter, it should be reaching to that first line past the tall one, but not past that first line. It should be very close to right on it. If it's 1.2, then it should be right on the 2 or very close to it. But that's not the smallest measurement we can get out of this, because it's not like we're complete idiots. You can see, for instance, between the 7 and the 8, there's 10 places as well. The first one being 7.1, 7.2, 7.3, 7.4, 7.5 being the middle one. That's the one with that elongated bar. And then 7.6, 7.7, 7.8, 7.9, and 8.0. So that's what they represent. But if you measured something and the end of it came up between, say, 7.2 and 7.3, then you could probably guess whether it's 7.21 or 7.29, right? You could tell the difference between 0.1 after the 2 mark and 0.9 after the 2 mark. You might even be able to tell between 0.1 and 0.3. So that's a difference of 0.02. So you'd say the uncertainty is half of that, because you're going to record numbers as your best estimate of the value plus or minus an error. So you'd say the error uncertainty for this particular measuring device would be a 1 in the second decimal place. So let's say you're measuring something like a rectangular solid. And let's say it's not that beautiful of a rectangle. Maybe it's made of gravel or concrete, so it's got little crooked edges. I'm going to call this the width. I'm going to call this the length, and I'm going to call this the height. Now, if it did have slightly varying measures, the best thing you could do is use this measuring device to measure this distance several different times at several different places. And then what you would report is W is equal to maybe 3.14 centimeters. Now, what that is your average of all the trials. Okay. But you also know that this measuring device has an instrumental error of at least 1 in the second decimal place, because you probably cannot tell the difference between 0.01 and 0.02. Or it definitely, I mean, you couldn't tell the difference between 0.01 and maybe 0.03. Cut that in half, you get the 0.01. So we'd write this as an uncertainty of plus or minus 0.01 centimeters. So in physics and science, you should record numbers as an estimate of the best possible value plus or minus some uncertainty. Now, ideally, if you'd taken several measurements, then this number right here would be called the standard error. And it hinges a lot on stuff you might have learned in the statistics class. I'm hoping you've learned it. This would be called sigma W, for instance. Now, what I mean by that is when you're reporting this number, we not only want to let people know what our best estimate of the number is, we also want them to know how confident we are that's right. So the way you can do that is you can take and let's say do 25 trials across here, take the average of that, that's what's going to go here. And then you take the standard deviation, okay? Now the standard deviation, which is given the symbol S, is a way to measure how far off on average your values are to the error, to the average. That's what it's for. Well, if you just sort of took this 3.14 minus each trial and then added them all up and divided it by the number of trials, you would inevitably always get 0 because there's just as many below as there are above, and the summation gives you 0. So the way to get around that is, instead of comparing the average to each individual one, you take the average minus the individual one and square it, because then it'll be a positive number. Now, if you do that, now you're going to have something with units of centimeters squared instead of centimeters. So that's not that helpful. So you're thinking, I better take a square root of that at some point. But also, it turns out if you want the numbers to work out right, even with a small number of trials, say like 25 as opposed to 100, then you don't want to divide it by n, you want to divide it by n minus 1. So really what we're talking about is we're going to take x bar minus x1 squared plus ... on up to x bar minus xn squared. And instead of dividing that by n, we're going to divide it by n minus 1, because it turns out that the numbers work out really nice that way. So for each of the trials, I didn't have much room, so that's why I only showed 2 of them. But for each of the trials, you're going to take the mean minus your trial, you're going to square it, and then you're going to add it to all the other ones just like that. You're then going to divide that by n minus 1. So if you had 25 trials, you divide it by 24. And then you're going to take the square root of it. That's the standard deviation. And what the standard deviation means is that if someone did an infinite number of trials with this experiment, about 68.5%, and I might be misremembering that number, but I think you are familiar enough with it if you've ever had any exposure to physics, to statistics, like 68.5% of those trials would come between this and one standard deviation, not standard error, okay? So that tells you how the trials will go, but what you really want to know is, how would an infinite number of experiments stand up? Okay, how does this stack up to an infinite number of experiments? Well, that's something called the standard error. So that standard error, we'll use a symbol like sigma sub w, where w is the variable you're talking about and sigma represents the standard error. But that's also called the standard deviation of the mean. Okay, in other words, this process that we just did with this, we're going to do that exact same process. Instead of doing it on the mean versus the individual trials, we're going to do it on the mean versus the individual means of all the other experiments. In other words, we're going to take an infinite number of experiments and see what their results are, and take the average of all that infinite number of experiments and say x average minus one experiment, x average minus experiment 2, x average minus experiment 3, x average minus experiment 4, square all those, add them all up, and then divide. This time, since you're doing an infinite number of experiments, you can actually get away with just dividing by n instead of n minus 1. And lo and behold, what you end up getting is x bar minus x1 squared plus x bar minus x2 squared plus ... plus x bar minus xn squared, square root n minus 1 from the first standard deviation that we calculated times n. So you can see it actually is just the standard deviation S sub w, or S sub x in this case, S sub w divided by the square root of the number of trials. So that's the number that's supposed to be reported here. And what it means is we're saying, hey, I just did an experiment and I got that the width of this block is 3.14 centimeters. If an infinite number of labs did the exact same experiment, then 68.5% of them, let's say it's 100 million. If it's 100 million people did them, then 68,500,000 would get a value between 3.15 and 3.13. Okay, so again, it's that roughly 68% mark. The second one, by the way, if you go 2 standard deviations or 2 standard errors, you get 95%. And if you go 3, you get 90, it's actually 99.8% or something like that. So it's really, really high. But that's statistically what's done. So you should see that it's obvious that all experiments 1 are going to have some error. For instance, even if I was able to like zoom in on these little individual hash marks, and then I had an infinitely fine little knife, so I could cut 10 little divisions between 7.1 and 7. Between 7.1 and 7.2, then I would get an extra digit. But that's as far as I could get, and the uncertainty be 1 in that last digit. But I could maybe say, well, what if I go another size down? So I take each one of those little 10 marks and I zoom in on it and etch 10 little evenly spaced marks for that. Then I'd get another decimal place. Well, eventually you're going to get so small that you're comparable to the size of the atoms. And if you know anything about atoms, you know they're sort of jiggling around in a solid like this. So you're going to introduce some uncertainty because the atom's going to be wiggling. What do you call the end of the meter stick? Is it where the farthest that any atom reaches out to this edge at any one time? Or is it the nearest that any of the atoms come in at any time? Or is it the average of the distance? So there's always going to be errors in things. And what we have to be able to do in science is not only estimate those errors with tools like standard deviation of the mean, called the standard error, or by realizing the minimum uncertainty a device will have is 1 in the last decimal place, or by looking at the meter stick and saying, well, Mr. Younger, you're trying to measure this thing. Look how rounded that edge is. See how rounded that is? So I'm introducing a little error by trying to look at it along here and estimate it where it's correct. So this one I might have to say maybe the error is 0.05. And that's just me trying to reasonably estimate how precisely I can mark off this edge relative to the right mark on here. So that's another way of calculating sort of your error or figuring out what your error is. But the big thing is, what then do I do if I want to, for instance, do an experiment where I determine the volume of this thing? Then I've got a W that is some average plus or minus some standard error. I have an L that's some average plus or minus some standard error. And I have an H that's some average minus plus or minus some error. How do you do that? Well, we know that the volume, which is really a function of W, L, and H, we know that formula is W times L times H. Maybe I've already got W. Maybe we found that L was equal to 2.87 plus or minus. Oh, let me go ahead and write centimeters there first. Hold on. Centimeters plus or minus 0.03. Maybe there was some more difficulty in measuring that one, or the standard error actually gave us a bigger value because it was more crumbled up along the edges. And then we had, say, H was, let's say, 2.91 centimeters plus or minus 0.02 centimeters. Okay. Well, if you want to know what the error in the volume is, You'd say, well, what is the thing that comes after the plus or minus when I write up my lab report and go submit it for publication? What am I going to tell the world that my volume is? Well, I'm going to say my volume's best estimate just like when we took 25 trials, we took the mean of those. That was our best estimate. Well, now we're going to do the means. We're going to say W bar times L bar times H bar, where you put a bar over something, that just means the average. You could also use this symbology, which is like W in brackets times L in brackets times H in brackets. All those mean the same thing. So that's what you'd report in front of the plus or minus. But what would you report after the plus or minus? Well, one way to think about this is, according to these numbers, we expect the volume absolute largest, so V largest, would be equal to 3.14 plus 0.01, so that'd be 3.15 centimeters. And the L would be 2.90 centimeters, because that's 2.87 plus 0.03. And then the H would be 2.91 plus 0.02, so that'd be 2.93 centimeters. And then we do the math on that, and we're going to say 3.15 times 2.90 times 2.93, and I get 27.76555. 26.7655. Let me get rid of this real quick. And I'm writing all the digits because we really don't know where to round this to yet. And notice what happened to the units. The units actually multiplied by each other, so it became centimeters cubed. Now I might say, well, the absolute smallest it could be would be when you subtract the standard error from it. So 3.13 centimeters times 2.87 minus 0.03, that'd be 2.84. And then times 2.91 minus 0.02, so that's 2.89 centimeters. So now I'm going to say 3.13 times 2.84 times 2.89. This one I get 25.68, 25.68979 cubic centimeters. Okay. So if we think of numbers as being something you report as a best plus or minus one number, then you'd really want to choose the number dead center, which obviously should be what you got when you multiply the averages together. But then you'd cut the distance between the two ends in half. So if I took V largest minus V small, so V large minus V smallest over 2, that might be an estimate of what the error should be. Okay. In other words, that's just throwing it out there and seeing this might actually be pretty good. So let me now do that. I'm going to take 2.7655 minus 25.68979, and I get 1.075762 over 2. So I say divided by 2. And I got 0.537881, 0.537881 cubic centimeters. Okay. So what that's suggesting is I have an uncertainty of at least 5 in the first decimal place. So what I'm going to do is I'm going to take the averages, which is a 3.14 times a 2.87 times a 2.81, or excuse me, 2.91. So 3.14 times 2.87 times 2.91. That's my best estimate. So I just took the original numbers. You can see it right there. I just took the original numbers and I'm going to multiply them. And I get 26.22, but I have an uncertainty of 5 in the first decimal place. So I'm going to report the volume to be 26.2 plus or minus, and I'll keep the units completely outside this time, plus or minus 0.5 centimeters cubed. So that is, at least in some sense, a reasonable estimate of what the error might be. Well, it turns out it's not a very good estimate. In fact, we do a lot better than that in experimental design. But that is to give you some idea what we're talking about here. That's showing you what it means to say error propagation. So when you measure a certain number of variables like W, L, and H, and then you use those variables to calculate some other quantity, that new quantity is going to have an error in it. And this is one way of estimating it, but it turns out to be way too large. That's way too large of an estimate. In fact, the way we do it is this. If you think about it this way, you look at, for instance, X, and this is f of X, right? You know, if you have a certain amount of error in X, so this much right here is sigma X, and this would be X itself, right? If the function did something like this, this would come up here, this would come up here, and that would come up there. So that uncertainty, sigma F, is going to be sigma F equals the absolute value of df over dx times sigma X. That just makes sense when you look at it this way. Well, if you think about f of X being a function of X and Y, it'd be f of X and Y, there'd be a Y axis maybe sticking into the page, and then the Z axis pointing up. Then you could get a more general result, which basically says, hey, the uncertainty in a function f is equal to the square root of the sum of the squares of, now this is a weird looking thing. You might not have seen it if you've only taken out calculus 1 yet, but I tell you, it's not hard at all. But you take the derivative of f with respect to x1, and then you multiply it by the error in x1, and you square that, plus to take partial derivative of f with respect to x2 and the uncertainty in x2, and you square that, plus dot, 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 on up to however many variables you have. And that is the proper error propagation formula. Okay. That's not what you learned in lab. Probably today you talked about percent error, percent difference, and sig figs, right? Did y'all do that in lab today? Anyone?
Yeah, that's what we did.
Okay, so that is sort of the kindergarten version of this. Okay, but it's normally what we learn in our first chemistry class. It's normally what we learn in our first physics class, is using sig figs. And you're going to use those for some time in your lab, but eventually you're going to get to using this. So let me show you an example. Let's say I'm going to do exactly the volume formula, but instead of using width and length, and well, no, I'll just go ahead and do it. Let's say volume is a function of width, length, and height, and that function is W times L times H, right? Well, this derivative is just like a regular derivative, except what you mean is you're pretending like all the other variables are constants. So when I say the partial of V with respect to W, I'm pretending the L is like 2 and the H is like 4. So what is the derivative of 8W with respect to W? 2 times 4 is 8. That's where I got it from. So this is like 8w. What's the derivative of 8w with respect to w? 8. Yes. So the 8 really was L times H. The partial derivative of V with respect to L, now it's like the W is a 2 and the H is a 4. So I got 8L. Again, you get the same derivative, except now it's W and H. And you take the partial of V with respect to H, and you get WL. So see how you're just pretending all the other variables are constant? That's all a partial derivative is compared to a regular derivative. Okay. So now I can plug that formula in. I'm going to say the uncertainty in V is equal to the square root of L squared H squared sigma H. I don't know why I wrote X there. Sigma H squared plus W squared H squared sigma L squared plus W squared L squared sigma. That was supposed to be sigma H. This other one was supposed to be sigma W. Maybe that was why I was writing it wrong. Notice this one goes with the W, so that should be sigma W. Okay, now that is actually a correct formula, but it's not a very convenient form. So if I introduce another quantity called the fractional error, we can get a real simple result. The fractional error has a symbol that looks just like the formula. That's the symbol for it. So I'll put quotation marks around it so you know it's a symbol. Well, the formula is literally you just take the uncertainty in V and you divide it by your best estimate of V. Well, that means I'm going to take this thing and divide it by W times L times H, and I understand that it's supposed to be W bar, L bar, H bar. And since this is all under the square root, I'm going to put it under the square root, which will make it squared, and I'll get L squared H squared sigma W squared plus W squared H squared sigma L squared plus W squared L squared sigma H squared. All of that divided by W squared L squared H squared. So I literally just took and divided it by, again, technically these are just W bar, L bar, and H bar. But because they're that's what these things are supposed to be too. This is really just L bar, and this is literally just H bar, W bar, H bar, W bar, H bar, right? Now I can make some cancellations. Notice the L and the H cancels out in this term. So I end up just getting sigma W over W squared. Notice the W and the H cancel out here. So I end up getting sigma L over L squared. And notice the W and the L cancel here, and I get sigma H over H squared there. So it turns out the fractional error of any product, X times Y times Z, or X times Y times Z times W times Q, always are just going to be the sum of the squares when you're multiplying or dividing. So this formula will hold true as long as there's no numbers. It's just like V times or W times L times H over, say, X times Y. You're just going to have sigma W over W squared plus sigma L over L squared plus sigma H over H squared plus sigma Y over Y squared plus sigma X over X squared. Square them, add them all up, and then put square root over it, and you've got the fractional error of whatever that quantity was. So even though we derived it for the special case, you're going to show later that it's true for all multiplication and division problems. Similarly, if we had something like f of X and Y is just equal to X plus Y, then the partial of f with respect to X is when you pretend Y is a constant. So X plus 3. What's the derivative of X plus 3 with respect to X? 1. And what's the partial of f with respect to y? In that case, you pretend x is like a 2 or 3 or whatever. So the partial with respect to y is 1 again, right? So if I take that formula up here, then that says the uncertainty in f is equal to the square root of sigma x squared plus sigma y squared. It's technically times 1 squared, but you don't even need to include that. And it turns out that this is true for x plus y. It's true for x minus y. It's true for if you had x plus y plus z plus q, you just have one of these for each of those variables: sigma x squared, sigma y squared, plus sigma z squared, plus sigma q squared. And it's also true for subtracting all of those, just like this would be true for x, y, z over w, l, h. I would find that sigma f over f is equal to the square root sigma x over x squared plus dot, 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 plus sigma h over h, sigma h over h squared. As long as you did one for each one of those variables, it'd be golden. So that's actually the way error propagates. Now you can see that that can be a bit of a problem, because in doing this, what you're going to have to do is you take that original data we had, and we're going to have to take the sigma w, which was 0.01. We're going to divide that by 3.14, and that's what goes in there, and I square it. Then I'm going to take the 2.87 and divide that into 0.03 and square it, and that goes there. And then I take the 0.02 and divide it by 2.91, and that's going to go in there, and I square it, take the square root. And what that's going to give me is the fractional error of the volume. But I want to know what comes after the plus or minus. Well, that's when you have to use this formula and basically take that fractional error and multiply it by the 26.2 that we got. And generally, we're going to report the number that comes after the plus or minus. That's always going to be one digit, 190 digit. The only exceptions to that is if you have like a 1 and then the next digit is like 4, 5, 6, 7, 8, or 9 or something. A lot of people will take the time to write 1, 4 or 1, 7, because that 7 is a huge fraction of the 1, and you're sort of selling yourself short. But the main thing to realize with all this is that digit in the uncertainty is lined up exactly with the last digit that you round your number to. So the fact that that 0.03 was in the hundredths place is why that's rounded to the hundredths place.
I have a question.
Yes.
So the standard error for each of these like values, basically when you're talking about the error propagation like expression with the square root, what's going in that place is if we're not giving like a measurement uncertainty that's like what we're supposed to use in the lab, we have to calculate that by finding the standard error of that, like
of those trials.
So yes. Okay, so we find the standard error first, and then we just integrate that in the error propagation later.
Yep. And actually, you first find the standard deviation, because your calculator and also Excel, those things will do standard errors, or excuse me, standard deviations automatically. So you can play with yours with some data, find out what it's actually calculating, make sure it's calculating the over n minus 1 if you do it by hand. Then you'll know that's the standard deviation. And then all you have to do is take that standard deviation, divide by the square root of the number of trials. Right.
So will we need to memorize the error propagation for the tests? Or are we allowed to have
not
that?
For the face-to-face class until maybe the end of the semester, it might come up. But this type of formula you need to know. And we'll have a lab specifically devoted to that. Mr. Mitchell will give you a lab specifically devoted to that. And it might just be one where it's highly mathematical. We'll give you a buttload of data, and you make a handwritten table to find the mean and standard deviation. And then you use that standard deviation for those variables to get the standard error and so on and so forth.
Okay.
So someone is saying the camera is kind of blurry. So I'm going to zoom in a little bit to see that. And remember, these notes that I take today, they're going to be on my Google Docs. They'll be on my Google Docs almost immediately. The video won't be up for a couple hours on my YouTube channel, but they will be available. So if you are having a hard time seeing all this, don't worry, you'll be able to see it later if you either watch the video or just download the document. So that's really how error propagates. And if you actually compared that for, let's say, heck, let's go ahead and do it. And then I'll go ahead and give us a break. So let's say sigma v over v is the square root. Now I'm going to take our variables that we had, which was sigma w over w, that'd be 0.01. Notice the centimeter is going to cancel out with a centimeter in the bottom. So I'm not even going to bother putting the units, but the first value was 3.14. I'm going to square that. And then the next one was for the L. So that was 0.03 over 2.87. Sorry about that hideous looking 8 there. I'm going to square that plus the 0.02 over 2.91 squared. So now I can compute all that junk. Notice, I just wanted you to see where those numbers are coming from. They're coming from, the bottom is the best estimate, the 2.91, the 2.87, and the 3.14. And the numerators, the 0.01, the 0.03, and the 0.02. So that's why I brought that data back to you. Now I'm going to calculate that, and I'm going to say 0.01 divided by 3.14. Oh. And now I'm going to square that. So that's 1.01 times 10 to the negative 1, 2, 3, 4, 5 times 10 to the negative fifth. This one would be 0.03 divided by 2.87. And now I'm going to square that. And I get 10 to the negative fourth on this one. And that one had 4 decimals. Yes, it's in there. Okay, that works. Now I'm going to do the 0.02 divided by 2.91. Now you can see that I've actually did what I was saying. I calculated the 0.01 over 3.14, and then I squared it. That's where I got that. Here's the 0.03 over 2.87, and then I squared it. That's where I got that. And now I'm going to do this one, and I'll say enter. And now I'm going to square that. And I get 10 to the negative fifth. So that's 4.5 or 4.72 times 10 to the negative fifth. And now I add those things and take the square root, which luckily I can just scroll up and say, this one, enter. This one, enter, or plus, enter. I got to put plus in there. There you go, that works. And now I can go up and take that last one and go here and put plus, and then I take this guy and say enter, and I get 0.0001666. Now I got to take the square root of that, and that gives me 0.012909. Now this is a 2 after the 1 that came out. So I would definitely not take the time to add the extra digit there. We can see the fractional uncertainty is really 0.012909. but that's the fractional uncertainty and has no units. So the uncertainty in the volume is equal to the fractional uncertainty times the best estimate of the volume. So now I got to take that value, which is a fractional error, 0.012909, and I'm going to multiply that by my best estimate of the volume, which was 26.2. I'm going to carry the extra sig figs though, so I got to scroll up on my calculator and see what that actually turned out to be. 26.22434. Centimeters cubed. Now it's going to actually have units. So notice I went up there and found that 26.22434. So now I'm going to take that, enter, and multiply it by that 0.000166. Excuse me, no, times the 0.0129. And I get 0.3. So the error in the volume is 0.338536. I'm just showing you that so when you try to verify this, you get all the same digits, you'll know you did it right. So really, at the end of this experiment, what I should report in my paper would be that the volume of this block was, notice it does line up in the first decimal place. That's where the leftmost digit is. So that's where I got to round the number to. Because if I'm uncertain by 3 in this digit, I have no clue what these digits are, right? So that's why I'm going to have to round it to 1 decimal place. And I already did that before. So it's going to be 26.2 centimeters cubed plus or minus 0.3 centimeters cubed. Now notice this is markedly better than what we got by doing that, biggest minus smallest. We got 0.5. We still got a pretty good sized number, but 0.5, it wasn't. So it actually did improve. We got a smaller or more narrow and more correct percent error, our error in the volume. So that's the robust way of doing error propagation. Someone asked about the numbers, so I'm going to bring it up closer to you. Can you see that now?
I have a question.
Yes, Nora.
So for
All right,
that last part, when you multiplied the best estimate, what did you add to the best estimate?
I just added the rest of the digits.
Oh, okay. Are we supposed to do that, like put the actual number in, or could we have just done 26.2?
You always need to carry at least 1 extra sig fig on intermediate calculations.
Okay.
So you didn't necessarily have to put 26.2. You could have put 26.22. That would have been fine, or 26.224. That would have been fine. But I wouldn't have just did that because that makes you rounding twice. You really only want to round once, and that's at the very end.
Okay. All right. Okay. Thank you.
No problem. So that's really how you're supposed to do error propagation and how you're supposed to round off your numbers. You're not supposed to use sig figs, which, by the way, if we did the sig fig rule, notice W, L, and H all had 3 sig figs, right? And the sig fig rule, when you multiply or divide, is the part of the multiplication or division problem that had the fewest sig figs has the number of sig figs that the answer should be rounded to. So this answer should be rounded to 3 sig figs, which is, lo and behold, exactly what we got in this case. And that's exactly why we can use sig fig rules, is because a lot of times they're pretty close. Now, when you're adding numbers, which you learned this also in lab today, you find the number that has the most number of decimal places and you round it, or excuse me, has the least number of decimal places, and you round the sum or difference to that smallest decimal place. Okay, so if you added a number with 3 decimal places to a number with 1 decimal place to a number with no decimal places, you add those and you have to round it to the nearest whole number because the one with no decimal places is the least known one. And finally, if you have a function of 1 or 2 numbers, then whatever numbers you're putting in it, however many sig figs that has, the one with the least tells you the number of sig figs that go in the answer. So if you took the inverse tangent, for instance, of 3.14159, which has 6 sig figs, divided by 2.8, which has 2 sig figs, then you'd have to round the answer to 2 sig figs. So that's the sig fig rule. But the real way is, like I said, doing all this stuff, this calculus that allows you to actually calculate where the error is. So let's take classes over at 7:50, but I'm going to go ahead and give you guys a 10-minute break. So let's meet back here at 7. Right now, my clock says it's 7:10. So let's meet back here at 7:20. Okay, I'm going to leave it on. So if anybody has any questions, you can. And somebody try to remind me to turn the recording back on if you don't mind. So does anybody have any questions while we're taking our break? Recording again. So we've covered a lot of stuff right now. Does anybody have any questions about what we're doing? Again, you're going to have a whole lab on this stuff. I'm giving you an intro to it right now, but you will have a lab later, and it'll be somewhat numerical. It'll be somewhat calculus definitions and derivations you got to do. But the main thing is it's the standard level of science analysis that you're supposed to do if you're going to be an actual science major. So recently we discovered that our lab for physics 242 and 241 wasn't transferring to UVA, and might not be for Virginia Tech either in the near future, except at one level. So they have like 2 tiers of lab for this course. One tier is for the science majors, and one tier is for the engineers and physicians and, you know, pre-med, that sort of thing. The ones that the scientists take require them to do this and a lot of writing. So we're slowly, I've been integrating it for a long time myself anyways, but as a department, we hadn't done that until I recently became chair. And now we're doing that to bring on error analysis and propagation of error. So if you're, yes, go ahead.
So did you say this class doesn't transfer?
It actually, the whole thing transfers, but you get in that second tier lab for the lab portion as opposed to the first tier. So if you're, you know, going to UVA or Virginia Tech and you want to major in chemistry or physics, they might make you repeat this lab. But if you're going to major in some engineering or in pre-med or biology, they will take this one right out. But it still transfers period as the lecture portion. It's just the lab portion might go down as the second tier lab, not the first tier.
Okay, thanks.
Are you thinking about majoring in science, or are you majoring in engineering or something else?
I'm an engineering major at Virginia Tech.
Okay.
And I needed the lab and lecture portion of this class to apply for my major. I've already finished my first year.
Gotcha. Yeah, then you'll probably be fine. I don't think Virginia Tech has started doing it yet. They're just taking ours on, but I expect that might happen in the near future. It happened last semester with UVA, so Virginia Tech might be in the near future, but I suspect it'll count for yours either way.
Okay, thank you.
Okay, no problem. All right, so that's the propagation of error. Your book talks about it a little bit. It barely just mentions the idea of quadrature, and that's that summation, the square root of the summation of the squares. And it actually mentions scientific notation and sig figs and all that good stuff. Really, though, what we need to go on to next is understanding the systems of units that we use. So we use something called the System International, SI system, or the metric system is what most people are used to calling it. And that's the units that we use. In fact, the actual units that we use in America, which us and I think Liberia is the only other country that uses it, is called the British system. So yeah, the Brits don't use it either. And it's based on the pound as a unit of weight, not mass. The inch is a unit of length, and the second is a unit of time, whereas the SI uses the MKS system, which is meters, kilograms, and seconds. So it's kind of weird thing, the kilogram, because the kilogram is a normal mass thing. A gram is a very, very low amount of mass. So they didn't want to use the standard as the gram. They made a standard in terms of a kilogram. And in deciding what that was going to be, they chose a metal called platinum iridium, which is a mixture of platinum and iridium. And that particular metal is not very corrosive. So it's if you subject it to air, it's not going to pick up a lot of oxidation or anything like that. So it's really ideal in that sense. But also what they did is they took it and made it into a cylinder, and the cylinder, you know, has a radius R and a height H. That is a shape that you can minimize its surface area with, and that's the extra credit problem you can do this time. I'm going to post it as an extra credit assignment at the bottom of week 1's module. But what you can do is take the surface area of a, here you go, let me draw it right here. So you're going to take the surface area of a cylinder. So the cylinder is like this. It has a radius R like that, and it has a height H like that, okay? The volume of such a shape is pi R squared H. The surface area is 2 pi R, that's the circumference, multiplied by the height. So if you actually rolled out a soup label off of a soup can, then it would be a rectangle whose height is H and whose length is 2 pi R. So this is 2 pi RH, that would be the area, plus the end caps, which is 2 times pi R squared, okay? So they basically have platinum iridium, which means the density equals a constant, fixed value. And since the volume depends on R and H, it's going to have a constant value. So the V is actually going to be a constant, but R and H have to be related through these expressions. So what you can do is you can solve the V expression for, say, H, and substitute that formula into S. If you do that, then you'll have S, the surface area, in terms of R and V, but V is a constant because the mass has to be a constant. The mass is the standard mass, 1 kilogram. Those two constant, and the fact that density is equal to mass over volume means that the volume has to be constant. So by submitting a formula involving V for this H, you've gotten rid of the H dependence, and you only have a R and V dependence, and the V is a constant. So if you want to minimize this, does anybody know what you do in calculus to maximize or minimize something? Anyone? Bueller? So in your first semester calculus, one of the first applications you learned of derivatives is you can maximize and minimize things. And you do it by setting the first derivative equal to 0. So ds over dr equal to 0. Notice I didn't have to write a partial there because I've not gotten rid of the H. It's no longer a function of 2 variables. It's a function of 1 variable. The variable is R. So if I take that derivative, set it equal to 0, and solve for, for R, then I'll get an R as a function of V. Okay. In other words, you'll have R in terms of V, which is there. Okay. Now you had solved that V for H and plugged it in here to get rid of the H. So when you're done with that, you'll have this R value that is either a max or a min. So we'll call it extrema. So EXT. You will plug in that volume and eliminate everything but the that can get eliminated, and out will pop an expression for R in terms of H. And you'll get R equals a function of H. So it'll be R is like 2H plus 1 over RH squared or something crazy like that, right? Well, that establishes that the surface area would be an extrema, and you know, an extrema could be a minima, like y equals x squared has a minima x equals 0, or it could be a maxima, like y equals negative x squared, or it can be an inflection point, like y equals sine x. Okay, now what you then do is you take d2s over dr squared and compute it at r equals f of h. In other words, whatever you found when you put the v back in and solved r for in terms of h. And if you get that this is positive, it's a minima. If the second derivative at x equals 0 was a negative, then it's a maxima. And if it was 0, it'd be an extrema. So your extra credit assignment is just this. You're going to do everything I just told you there, solve this for h to eliminate h, take the derivative of this, set it equal to 0, solve for r, then substitute v back into that expression for r, so you'll have r in terms of h, and then take the second derivative with respect to r. But before you do that, okay, take the second derivative of this function with respect to r, and then plug in that special value of r and see if it comes out to be positive or negative or 0. Okay. Now you do that, you take a photograph of it, maybe import it to Word and make a PDF, or if you have the application on your phone, you can just take the photograph of it, make sure it's clear, and send it, post it on that assignment as a PDF document. Okay. So that's one of the things about the system of units is we have these fundamental things that are considered to be the standard. And what we do with mass is every now and again, you'd have to actually take it out of this protective area where they keep it at a fixed temperature, fixed humidity, all that good stuff. They keep it under several nested glass bottles, jars basically, with like 0 air pressure in it and stuff like that. And about once a year, they'll pull the actual master out and compare it to some standards that other countries want to use. Or maybe every a couple times a year, they'll pull out its replica and let other countries compare that. But if anything were to happen to that, we'd have some difficulty in reproducing it. So ideally, we don't want the standard of measurements, for instance, the kilogram, we don't want it to be something that is at a single item in some single country, because that could screw up everything. We haven't yet figured out a way to make this item independent of a specific item, but we have done that with length and time. So for instance, in the SI system, we realized that the speed of light, is 299 million. 792,458 meters per second. And it used to have some decimals after that and stuff like that. But what we did was we first said that the fundamental unit of time, 1 second, was in fact the time required. Initially, it was 1/86,400th of a mean day, but now it's actually defined quite a bit differently. It's defined in terms of radioactive decays, and I think it's right here. Yeah, it is. So when cesium-137 has decayed 9,192,631,770 times, a single second has went by. So now we've got a time that anybody can measure. All they have to have is a Geiger counter that's really fast. So you put a sample of cesium-137 in this type of Geiger counter, and as soon as it gets to 9,192,631,770 decays, then you know 1 second has passed. So that's our standard unit of time. Then, since we had that standard unit of time nailed down so good, we now call the meter as the length or distance light travels. In 1/299,792,458 of a second. Okay, so that's the new standard of the meter. It used to be a platinum iridium rod as well, which is another cylindrical shape, but it had 2 little etch marks in it, and they would take it out and you could compare the ends of your, say, meter stick to the etch marks. But they've got rid of that standard now, and they just say, okay, if you watch light travel for 1/299,000th or 1,792,458 of a second, then that distance traveled was exactly 1 meter. Okay, so that's the way the modern system of units are. We also use the prefixes, which you can make up your own mnemonic, but here is the prefixes: T dot dot, G dot dot, capital M dot dot, K, H, DA. This is the base. And then deci, centi, milli, dot dot, micro, dot dot, nano, dot dot, pico. And what this represents is each one of these is a power of 10. So this is 10 to the 0, which equals 1. 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 6, 10 to the 9, 10 to the 12. This is 10 to the -1, 10 to the -2, 10 to the negative, whoa, 10 to the -3, 10 to the -6, -9, and 10 to the -12. So you can use this and all these dots. Like if I tell you a number is 0.000000000000581, let's say teragrams, and I would like to convert it to micrograms, then I go on here and I say, okay, well, how many moves? That's the key thing. How many moves and in which direction? Well, what do I mean by that is, okay, let's start on the tera, because that's the unit I'm at. There's 1, 2, 3. See, I'm counting the moves, not the endpoints. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I got to move the decimal place 8 to the right. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that would be 581,000 micrograms. Okay, so that is a way you can use that table, but really that's usually for people that aren't very well adapted to mathematics. There's another way we use units of conversion, and that is by multiplying by 1. So what you got to remember is 1 is, of course, 1/1. but it could also be 3.14159 ... over 3.14159 ... As long as the top is equal to the bottom, it's still 1. So you could also say, well, wouldn't this also be true? 1 foot over 12 inches, that's 1. So is 12 inches over 1 foot. So whenever you're asked to convert a unit, all you have to do is multiply by 1 such that the unit you have disappears and the unit you want is what's remaining. So let's take, for instance, 60.00 miles per hour. Okay, notice how I wrote miles per hour. You can also write it as 60.00 miles over 1 hour, and that's fine too. So when you're doing a unit conversion, I normally recommend you first write the number as a fraction with at least 1 in the denominator. If you have a denominator unit, then you can put that unit down there too. But if you don't, just put it over 1 so you don't get confused in your process. Now, this is sort of the most awesome of conversions because it actually converts it to an exact explanation. In other words, 60, if I had this as all zeros to an infinite number of decimal places, then the answer would be right to an infinite number of decimal places. So what I'm going to first do is I realize that 1 mile is the same thing as 5,280 feet. And notice that mile can cancel out with that mile. So now I have feet per hour. Now I also know that 1 foot is equal to 12 inches. So this foot will cancel out with that. Notice how I did the mark through a different way. Each time you do it, you want to use a different mark so you can look back and see if you made any mistakes later. Now I'm down to inches per hour. Well, I happen to know a conversion from the British system, which has inches, to the metric system, and it's an exact conversion, and that's 2.54 centimeters is equal to 1 inch. So I'll put 1 inch down here, and then I say 2.54 centimeters up here. That's an actual exact one. This one I'm going to cross out with an X. Now I've got centimeters per hour. And I really want it in meters per second. So I happen to know that there's 100 centimeters in 1 meter. So finally, I cross this one off with a wavy line from bottom left to top right. And I'm now to meters per hour. Now I could either convert the hours, which is in the bottom, to minutes and then to seconds, or I can just do it straight from hours to seconds because I know there's 60 times 60 or 3,600 seconds in an hour. I'm going to do that second one. So I'll say that 1 hour is equal to 3,600 seconds. And now this time I'm going to use a squiggly from the top left to the bottom right. And I see that the only units I have left are meters per second. So that works out well. Now, the way you do this when you do a long string like this, until you get really good at dealing with calculators and real numbers and calculating, I highly recommend you do this every time. So what I say to do is you multiply all the numerators and make a new numerator. So I'm going to do 60 times 5280 times 12 times 2.54 times 1 and times 1, and I get 9656064. 9656064 meters over 1 times 1 times 1 times 1 times 100 times 3,600. So that's 36,000 seconds. Now I divide that number by this number. And you can see on my calculator how I did it here. And it gives me 26.8224. Now I can actually write that to any number of decimal places I wanted if I really assumed that I knew it was exactly 60 miles per hour to an infinite number of decimal places. Since I only know it to say 4 sig figs, which is showing there, then I really should call this 26.82 meters per second. So that's the way we convert units in here. If you wanted, for instance, to do this one, you could say 5.81 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So times 10 to the 13th teragrams. And what that means is 5.81 times 10 to the 13th, or excuse me, 10 to the negative 13th. That was supposed to be a negative. And then tera is 10 to the 12th. So I'll say times 10 to the 12th. And you get basically 10 to the negative 13 times 10 to the 12 would be 10 to the negative 1. So that's 0.581, just plain grams. And now I could say, okay, well, I want it in micro. So 1 million, or excuse me, other way around. 1 million micrograms is equal to 1 gram. Okay, and that's because the micro is 10 to the negative 6. So I could now just multiply this by 1 million, and you'd see you get the exact same thing we had, which is 581,000. So you can do that with those two, and that's really what this mnemonic helps you do. I would suggest you create your own mnemonic for this, but remember those dots because they have to be there. All right, so that's converting units. There's another tricky conversion that you have to know, and here's my best example of that. We know that the density of water is 1,000 kilograms per cubic meter. Now, a meter is about 39 inches. It's a little bit bigger than a yard. It's about the height of a doorknob to the top of the doorknob. That's about a meter. Okay. What I'd like to do is convert this to grams per cubic centimeter. Okay. So what I know is that 1 kilogram is equal to 1,000 grams. And what I also know is that 1 meter is equal to 100 centimeters. But that only gets rid of one of the meters. So I need another one. And now I've gotten rid of m squared, but I still have another value of m. So I have to do it a third time. And you can see basically I'm going to multiply by 1,000. 1,000 times 1,000 is a million. And then I'm going to divide by 100 times 100 times 100. That's a million. So I end up getting 1.000 grams per cubic centimeter. Anybody know the conversion between kilograms and pounds roughly?
2.206.
Yeah, good job. So yeah, if this is 1,000 kilograms, then that's about 2,206 pounds. Well, that's called a big ton or a metric ton. So 1,000 kilograms is equal to a large ton or a metric ton. Whereas that's equal to 2,200, I think you said 206 pounds. Whereas 2,000 pounds is called a short ton. Okay. And that's what we talk about, you know, here in America is the ton. When you say a 3/4 ton truck, supposedly that's supposed to hold 3/4 of a ton, which would be about 1,500 pounds. And that's what you can carry in the bed, not what you can tow. You can tow much more. So a 3/4 ton truck, which would be like, say, that's the 250 or the 2500 series, if I'm not mistaken. It's a 1/2 ton, 3/4 ton, and a ton, I think, but I might be off by one. So just imagine that those containers you're seeing riding around the roads lately, or you sometimes see them in people's yards, they're like, they got a metal fence around this white pseudo clear plastic bladder that's about 3 foot by 3 foot by 3 foot. That thing weighs literally a ton when it's filled with water. So that's kind of neat. All right, so that's the last of the unit conversions. And we got about 3 minutes left. So I want to do a little bit with dimensional analysis, and we'll talk next time about estimating things. But dimensional analysis is reducing, our unit analysis is reducing a variable like velocity to meters per second, or that's unit analysis. Or you can say length per time, and that's dimension. So if I told you that energy had units of mass, length squared over t squared, and I wanted you to find an equation for energy in terms of mass and the speed of light, which is also a speed, then you might say the unit of energy, which is equal to ml squared over t squared, is supposed to be equal to, let's say, the unit or the dimension of m raised to the n power times the dimension of c raised to the m power. So you'd say m is to the 1 power, l is to the 2 power, and t is to the -2 power. Then since mass is just m, that'd be m to the n, or excuse me, m to the little n. And speed of light is just velocity. So that's going to be L over T to the m power. So this side becomes m to the n power, L to the m power, and T to the -m power. Looking at these two, can you tell what n is?
One.
1. And what would little m be?
2.
2. So guess what we just discovered? E is equal to mc squared. And believe it or not, a lot of physics problems have been solved this way. You can use this to check your equations to make sure you remember them correctly. If you're trying to put a shot over the bow of some formula that relates, 3 or 4 quantities to some other ones, you can use dimensional analysis to figure that out. That's almost exactly what Schrodinger did when he came up with his Schrodinger equation. That's essentially what Bohr did when he came up with his Bohr model of the atom. He said, I needed this H constant. I know this constant had units of angular momentum. So he set the angular momentum equal to a whole number times H. And lo and behold, got the Bohr model of the atom. So all of this is what that's about. So next time I'll talk to you about estimating. Make sure you finish reading chapter 1 and preferably have read chapter 2 before next time, because we're going to do all of chapter 2 next meeting. You guys are free to go. I will check the roll via the attendance in this. So I will see you all Wednesday at 5:30. I'll wait for the last person to leave in case anybody has any questions. Thank you for coming, everybody.
I have one question
Go for it.
about the textbook. So you said we can access the textbook through our Canvas site?
Through the Mastering Physics, MyLab and Mastering site. Once you pay for that, you can.
Okay, got you.
Does that make
Alrighty.
sense?
Yep.
You might actually be able to get it before then, because you actually are allowed a 2 weeks free trial. So don't not do your homework because you haven't gotten that yet. But all you have to do is either click on the MyLab and Mastering link in Canvas, or click on one of the MyLab and Mastering assignments in Canvas, and it'll take you there. That will give you a way to buy it right there, which that turns out usually to be a little cheaper than the bookstore. And you can choose to buy it with an ebook or without an ebook.
Okay. Is it do you know more expensive with the ebook?
Yes, it should be a little bit more expensive with the ebook than it is for just the homework license. But if you really want to cut some costs, you can feel free to buy the 3rd edition and then buy the access to to the website because really the third edition isn't significantly different. If I ever took a problem out of the book, I would give you a snapshot of it or something like that if you're using a third edition, because the numbers might be different, but basically the wording is the same. So you can usually find a third edition for pretty cheap.
Okay. All right. Sounds good. Thank you.
Right. You're welcome, Nora. Brian, you have a question?
Oh, yes. So for the textbook,
Mhm.
you said to access through MyLab and Mastering. You said what would be the access code to get a free trial for it?
Okay, so what you're doing with that is you can just click on, see right here where it says MyLab and Mastering. The access code is something you purchase. There's also a course code, but I never give you that because you're supposed to go through Canvas to get to it. That way it automatically takes those grades and puts them in my grade book. So you can either click on this or you can go to the actual home and then click on chapter 1 homework, and that'll take you there. It'll ask you to create an account, and it'll ask you if you have an access code. And if you don't, it'll offer you to buy one, or it'll offer you to do a 2-week free trial.
I see.
And then at the end of 2 weeks, it'll just stop working.
So I would have to access it through home.
Yeah, exactly. Don't go the other way. That you possibly could find it the other way, but that would mess up everything. So you only want to go through by clicking here, or like I said in this other module. If you go to modules for week 1, you'll see some homework assignments there. That's the only 2 ways you want to access it.
I see. Could you go over the going through home section real quick? Sorry.
Yeah, so I'm trying to. It's going really slow. Really, really slow. But the little dot's moving, so I assume something's happening. Okay. So there's your syllabus. There's a video on your syllabus that I think you'll enjoy. Here's access to my YouTube channel and my Google Docs. This will be where the practice tests are. This will be where the tests are. Even though they're listed as online tests, I'll be making new tests to give you face-to-face. You'll see this repost. It'll say chapter 1 conceptual. You click on that and it'll have the due date, and it'll also give you that chance. If you haven't already registered with MyLab and Mastering, it'll first make you do that before it lets you conduct the homework.
For chapter 1 homework.
So by Sunday of this week, 11:59 p.m. This coming Sunday, you will need to have chapter 01 conceptual, chapter 01 homework, chapter 02 conceptual, and chapter 02 homework done.
Okay. So I'm not seeing the I'm at home and I'm not seeing this portion with
do you
chapter
see
1
this part?
Lecture 114. I do see that part, but nothing under it.
Yeah, that's because I've got them hidden. These are old assignments. I have new ones that I got to put in here, so I made them hidden until I put the right ones in.
Okay, so for this recording, like this lecture's recording, it will be posted under the
it'll be in my YouTube channel, and it'll have a name like PHY241N01C, and then it'll have 052322 in it.
Okay. So we'll just watch. So the place to watch your lectures is through YouTube.
Yes.
Okay. Thank you.
No problem.
Have a good day.
You too.